morning everyone. Welcome to A2Z Physics and Chemistry class. Today we are going to discuss about very important topic of class 12 physics, which is Kirchhoff's law. So scientist Kirchhoff, German scientist Kirchhoff in 1942 extended Ohm's law for complicated circuit and find out, and he also suggested the method to calculate current for a complicated network. Okay, so Kirchhoff's law. Actually, before going to the Kirchhoff's law, so we have to understand some new parameter, a new term, that is first your network or electrical network. Second, your junction, then loop, then branch. So, what is an electrical network? Electrical network is a complicated system of electrical conductor. Okay, it is a complicated system of electrical conductor. That means it consists of a number of electrical conductor in a very complicated way. Okay, the electrical circuit which consists of a number of complicated system of electrical conductor is called a electrical network. Then what is a junction actually? Junction means what? It is a point in the electrical circuit where two or more conductor or electrical conductor join together. It is a point in the electrical network where two or more electrical conductor joined. Okay. Then loop, or we can say this term loop, or mesh also we can say this term. Okay. So this is a closed path. This loop means actually a closed conducting path in an electrical network. This is a closed conducting path in an electrical network. Okay. Then branch. Branch means two junctions are connected by using branch. Okay, two junctions and in between two junctions there is a branch present over there. Okay, so these are the important terms related to the Kirchhoff's law, and the Kirchhoff's law is basically we can divide it into two important parts. The first part is called as the Kirchhoff's current law. The first part is called as the Kirchhoff's current law. Okay. Or we can say this is also, or in short we can see that this is KCL, Kirchhoff's current law. Okay. So according to the Kirchhoff's current law, the algebraic sum of all the current meeting at a junction is 0. That is, summation of I will be equal to 0. Okay. So let me draw a network actually. Okay, this network consists of four conductor having current I1, I2, I3 and I4. The direction of the current, or for knowing the sign convention for direction of the current, in this case the current which are meeting or which are going towards the junctions are taken as positive. So here I1 and I2 are the two current actually which are going towards the junction. That means here we can say this is I1 plus I2, and here I3 and I4 are the two currents which are going away from the junction, because this is the junctions. Okay, now we have to take negative sign over there. Okay, so that means the currents which are moving towards the junctions are taken to be positive, and the current which are moving away from the junctions are taken as the negative. Okay, as we know from the Kirchhoff's law, the net current is 0. So in this case I1 plus I2 will be equal to I3 plus I4. That means the net current entering to the junction is equal to the net current leaving the junction. Again repeating what is Kirchhoff's current law. According to this law, all the current meeting to a junction, or algebraic sum of all the current meeting to a junction is 0. that is summation of I will be equal to 0. So here the total current leaving the junction will be equal to the total current entering the junction. Okay, this Kirchhoff's current law is basically based upon the conservation of charge. Okay, then we are switching over to the second part of this Kirchhoff's law, which is called as the Kirchhoff's voltage law, or we can say this is Kirchhoff's loop rule also we can say. Okay, voltage law, or we can say this is loop rule. Okay, so this is called as the KVL. KVL in shortcut this is termed as the KVL. Okay, so first the law. From this law, this Kirchhoff's current law is actually applicable to a closed loop. So in a closed loop, the potential difference across a junction is 0, or we can say the summation of the EMF is equal to the algebraic sum of the product of the current and the resistance. That is, we can say V will be equal to summation of V will be equal to 0, or we can say we know this summation of E means this is V means this is IR, summation of E minus IR, we can say this is 0, or this is summation of EMF will be equal to summation of I into R. Okay, that means from Kirchhoff's voltage law we can find out the net potential across a junction will be equal to 0, or we can say the net EMF will be equal to, or the algebraic sum of all the EMF will be equal to the algebraic sum of the product of the current and the resistance in a closed loop. Okay, so now we have to, for discussing or for to know Kirchhoff's voltage law, we have to know some of the important sign convention for this. So for Kirchhoff's voltage law, we can choose any direction of transversal, that may be clockwise or anti-clockwise. Clockwise we can choose clockwise or anti-clockwise. Okay, that means the direction of transversal may be either clockwise or anti-clockwise. This is according to our, okay, we shall choose the direction of the transversal. Then the direction of the EMF. The direction of the EMF is always negative when it is going from the positive terminal to the negative terminal. Okay, when the direction of the EMF or the direction of the EMF is taken to be negative when it is going from the positive terminal to the negative terminal. Okay, suppose this is a circuit, then in this case what happened? This will be equal to negative, because in this case the transversal is from the positive to the negative terminal, so here E is taken to be negative. But similarly, the E is taken to be positive when the direction of the transversal, or when the EMF will be from the negative terminal to the positive terminal. So in this case, as we know, the arrow mark, this is from the negative terminal to the positive terminal. So in this case, the EMF will be positive. Okay. The third important and most important thing is that the direction of the current, or the direction of the product of the current and the resistance will be negative when, suppose this is a resistance, this is the current, and suppose this is the transversal. Okay, when the product of the current and the resistance is taken to be negative when the direction of the current and the direction of the transversal are opposite to each other. Okay, in this case we can take the product of the I and the R is negative. Similarly, if the product of the current and the resistance are taken to be positive when the direction of the current and direction of the transversal are taken to be in the same direction. Okay, so these are the most important sign convention for the Kirchhoff's voltage law. It is applied for a closed loop. Then let me explain by using an example. Suppose we can take a network. Let me draw the network first. Suppose we have chosen this direction of transversal. This is clockwise direction of transversal. This is according to our choice. whether we have to take the clockwise direction of the transversal or anti-clockwise. Here I have taken the clockwise direction of the transversal. Then the direction of the current. Suppose this is current I2, this is current I1, this is EMF 1, EMF 2. Suppose this is EMF 1. Now this is I1 plus I2. Now this is IR3 here. Okay, so in this diagram first we have chosen the direction of the transversal, that is clockwise. Then next is the direction of the current. In this case I1 is the current in this junction, there is in this branch, this is I2 is the current, and there is also this is I1 plus I2 is the current passing through the resistor R3. Okay, so here first we have to apply KVL. So how we are taking KVL in this case? Suppose first we have chosen this A, B, C, D, E, F. So suppose first we have taken ABCD loop. Okay, in ABCD loop the net EMF, first we have to choose the net EMF, because in this case the direction of the transversal is this is clockwise direction, and also the current will be also from the negative to the positive terminal. So here this is E1. Okay, but the net EMF which is E2, in this case this is the direction of the current is here and the direction of the transversal is opposite to each other. So here it is taken to be E2. Okay, so the net EMF will be equal to E1 minus E2. Now the current and the resistance product. In this case there is a resistance. Suppose this is R1 and this is R2, and here we have taken R3. Okay, so in this case the net resistance, the direction of the current as well as the direction of the transversal, both are in the same direction. So this is positive I1 R1. Okay, now next is here in the second resistor the direction of the current is and the direction of the transversal are opposite to each other. So this is I2 into R2. Okay, so here in the loop ABCD we have got that E1 minus E2 will be equal to I1 R1 minus I2 R2. Now we have to choose this FBCE loop. FBCE is also a closed loop, so here also we can apply the Kirchhoff's voltage law. So in this case only there is one EMF. So the first EMF is, in this case this is the direction of the transversal is clockwise, and also the direction of the current is also in the same direction. So E2, here we can choose this is positive E2. Okay, now the direction of the direction of the current is here, this is, and the direction of the transversal is in the same direction. So we can choose this is I2 R2. I2 R2. Okay, plus now in this case this is the I1 plus I2 is the current, and the direction of the transversal is also in the same direction. So here we can choose this is I1 plus I2 into R3. Okay, so this is for the loop FBCE. This is the EMF equation we can choose. So first we have got E1 minus E2 equal to I1 R1 minus I2 R2, and in the second loop we have got E2 equal to I2 R2 plus I1 plus I2 into R3. Okay, so for knowing the Kirchhoff's voltage law we must have to know the sign convention. Okay, so first the important point is that we can choose the direction of transversal, that may be either clockwise or anti-clockwise. And secondarily, this next important point is that the EMF will be positive or negative depending upon the direction of the current, or we can say when the current is going from the negative terminal to the positive terminal, E1 is positive, but the direction of the EMF is always positive when the current is going from the negative, when the EMF is negative, when the current is going from the positive terminal to the negative. Okay, now the product of the current and the resistance is negative when the direction of the transversal and the direction of the current is in the same direction, but no, it is in the opposite direction, but the product of the current and the resistance is taken to be positive if when the direction of the transversal and the direction of the current is in the same direction, but opposite direction the product is taken to be negative. Opposite, the direction of the transversal and direction of the current is when opposite to each other, at that time the product I2 R2 is chosen to be negative. Okay, so this is all about Kirchhoff's law. Kirchhoff's law is basically divided into two types: Kirchhoff's current law and Kirchhoff's voltage law, to solve or to determine the current in a complicated electrical conductor system. Okay, so this was today. Hope you enjoy my class today. Okay, so do subscribe my video, and thanks for